This is lesson 2.1, Operations with Matrices. In this lesson, we'll be looking at three things. We're going to start with just some basic operations that we can do with matrices, similar to the types of operations we do with real numbers. And then we're also going to revisit systems of linear equations, look at another way to represent those through matrices, and then finally finish up with something called partitioned matrices. So to start with operations with matrices, we're just going to look at how to add matrices, multiply by a scalar, and then multiply two matrices together. These may be things that you already know how to do, and if so, that's great. But otherwise, let's go ahead and dive in and show how this works. So for example, if I want to add two matrices together, we'll just make up a couple matrices here. One of the keys is the matrices do need to be the same size, so they both need to be m by n. In this case, we'll just use two by two matrices. And very, very simply, to add two matrices together, we're simply going to add the corresponding entries together. So we'll add first row, first column together, which in this case is 1, and then first row, second column together, and so on. So we'll add the 2 and the 1 to get 3, and finally the 4 and the 6 to get 10. So that's very simply how we add or subtract, if as it were, two matrices. Multiplying by a scalar, very, very similar idea. We're going to, again, we'll actually use the first matrix that we have there, the 3, -1, 2, 4. And to multiply by a scalar, in this case, -2, we're just going to multiply all of the entries by -2. So our resulting matrix, -6, +2, -4, and -8. And then finally, multiplying two matrices. Now this one, if you haven't learned this or if you haven't seen it in a while, this one just takes a little bit more thought. It's not quite as straightforward. And so again, I'm going to give just a little bit more in depth on this one, especially if you haven't seen this before. Basically, the way that this works is we are going to multiply rows of the first matrix by columns of the second matrix. So for example, let me go back to blue here. So a couple things. Because this is a 2 by 2 matrix and we're multiplying it by a 2 by 2 matrix, in order to perform the multiplication, the columns of the first matrix have to be equal to the rows of the second matrix. So these two numbers have to be the same in order to even perform this operation. What's going to happen is when we're done, the rows of the first matrix and the columns of the second matrix give us the size of our resulting matrix. So our resulting matrix, obviously being 2 by 2, is going to still be a 2 by 2. But if, for example, I took a 2 by 3 and then I took a 3 by 4, because these numbers are the same, the 3's on the inside, I can multiply these matrices together. And what results is a 2 by 4 matrix. Okay, so those are kind of the rules behind the scenes as far as whether or not you can go ahead and multiply two matrices together. So what's going to happen here is we're going to get a 2 by 2 matrix when we're done here. And like I said, we're going to multiply the rows of the first time the columns of the second. So when I multiply row 1 by column 1, that's going to give me the entry for row 1, column 1 in my resulting matrix. And very simply, I take the 3 times the -2, which is -6, and then I take the -1 times the 1, which is -1, and I add those together. So -6 plus -1 is a -7. And now I keep going. So now let me do this in different colors here. So now I'm going to take the first row times the second column, and that's going to give me the first row, second column entry. So in this case, again, just taking 3 times 0 is 0. -1 times 6 is -6. 0 plus -6 is a -6. Now we go to the next row. So now I'm going to take the 2, 4 and multiply that by each of the columns in the same way. So I'll speed this one up a little bit. So taking the 2, 4 times the -2, 1, the column in the second, I'm going to have 2 times -2 is -4. 4 times 1 is a +4. -4 plus 4 is 0. And then finally, the second row times the second column. 2 times 0 is 0. 4 times 6 is 24. And so I get 24 for my final entry. Obviously, if we had larger matrices, the same rules apply. You're always going to take the first row of the first matrix, so the first row of that first matrix, and then you're going to multiply it by all of the columns, and that's going to give you those first row entries. Then you're going to take the second row and multiply it by all of the columns, and that's going to give you your second row entries. And then you take the third row times the columns, and so on. So larger matrices, you're just going through that exact same pattern. You're just doing more of it. So that is how you do basic operations with matrices. So I've got an example here with some different matrices. And so if you want, you can go ahead and pause the video and just try all three of those and then start up the video again to see the answers. So for the first one, again, we're just going to add these together. I'm not even going to actually bother to rewrite these. We're just taking the 3 plus 3 is 6. The -1 plus -1 is -2. 2 plus 2 is 4. And 4 plus 4 is 8. Again, just adding the like. And I just noticed those matrices are the same. I didn't necessarily intend to do that, but that's fine. It still works. In the second one, we're going to multiply by the scalar of 3. So in this case, again, in fact, I'm not even going to, again, write this. We'll just do the answer here. Just multiplying by 3 gives us 9, -3, 6, and 12. And then for A, B, and I will write this out a little bit, just again to remind you, if you've not seen this before, kind of go through this one more time. So in this case, again, we're going to take that first row, multiply it by each of the columns, adding the results. So 3 times 3 is 9. -1 times 2 is -2. 9 minus 2 is 7. And then we've got 3 times -1 is -3. -1 times 4 is a -4. -3 and -4 is a -7. And now we'll go to that second row and multiply that by each of the columns. 2 times 3 is 6. 4 and 2 is 8 is 14. And then last column, we have a -2 and a 16 is also a 14. So that is our resulting matrix. So again, that's how we perform just some of those basic operations on matrices. So let's go ahead and look at systems again. We obviously looked at this in the last chapter and looked at how to use matrices, that augmented matrix with Gauss-Jordan elimination, to solve a system. And what I want to do here is just kind of show another way to represent a system like this using matrices. And we're going to consider the form AX plus or AX equals B. The idea being that A is your coefficient matrix, X is just going to be a matrix of our variables, and then B is a matrix of what the equations equal. So again, you've got to make sure those equations are in standard form, as always. But we're just going to write this with our coefficients first. So 3, 2, -4, -7, -5, and 2, and then 2, -3, and 7. And then we're going to write, we're multiplying it by x, and x again is just our variables. So in this case, we have an x, y, and a z. And then b is what the equations are equal to. So in this case, -12, -1, and 35. Now, before I go any further, just kind of to see what's happening here, if you look at these matrices on the left side, if we multiply those matrices together, you will get the systems, right? So if I take this first row and multiply it by this column, I get 3x plus 2y minus 4z, and then equals the -12 on the other side. So it's just another way to represent the equations using matrices, all right? It begins to play into what we're going to end with about partition matrices, but I don't want to get too far ahead of myself. Now, if we were to go ahead then and still use the techniques that we learned in the first chapter, if we set up our augmented matrix, I'm going to actually just go ahead and solve this. So I'm going to set up my completed augmented matrix. 3, 2, -4, -12, -7, -5, 2, and -1, and then 2, -3, 7, and 35. And again, if we were to just go ahead and use the Gauss-Jordan elimination method, that's going to give me a matrix that looks like this: 1, 0, 0, 2, 0, 1, 0, -1, and 0, 0, 1, 4. So we can see then that our answers are 2, negative 1, and 4. So again, kind of thinking about how we're writing these matrices, I could write this solution as something that looks like this. I could say that the matrix x, y, z is equal to the matrix 2, negative 1, and 4. Okay, or I could even just put this right back into that original equation, and I could write this whole thing out as 3, 2, negative 4, just again writing the coefficient matrices, or matrix, excuse me. And then we've got 2, negative 3, and 7. And then 2, negative 1, 4 is equal to negative 12, negative 1, and 35. Okay, so again, just kind of another way to think about writing this. Now, again, if I did matrix multiplication on the left side, 3 times 2 is 6. 2 times negative 1 is a negative 2, which brings me to 4. And then 4 minus 16 is negative 12, the answer on the right side. So again, just that idea that we can write our matrices A times X equals B, our systems, I should say, as matrices in that form. All right. So the last thing I want to talk about is what is called partitioned matrices. And, so we just looked at how to kind of write this really as these different matrices being multiplied and broken up into smaller pieces. And that's really what a partition matrix is. It's really just taking a larger matrix and breaking it down into smaller parts. So for example, one way we can do that is to write it as what's called a linear combination of column vectors or column matrices. And so I'm going to just start very generically and just, using our example, I can take each of these columns and just think of them as separate matrices, where the first column would be, for example, my x's. So I'd write 3, negative 7, 2, because again, those are the coefficients. The 3, negative 7, and 2 are the coefficients for x. And then plus y times the coefficients of y, which is 2, negative 5, negative 3. And then plus z, which has coefficients of negative 4, 2, and 7. And again, that's going to equal negative 12, negative 1, 35. So mathematically, again, all we're saying then is now we're really multiplying by scalars. X, y, and z are scalars. And if I take 3 times x plus 2 times y minus 4 times z, or plus a negative 4z, equals negative 12, that is just giving me this very first equation. So again, just another way to write this. In this case, though, what I've done is I've broken this down into these column vectors or these column matrices. And I don't really want to get too deep into this. What I really want is for you to just be aware that partition matrices exist. In small matrices like we're using in our examples, it wouldn't really make sense to partition a matrix, whether we partition like this in columns or in other ways. But I do want to just kind of talk a little bit more about this. So the idea, another way to think about this, is if I took that augmented matrix, and we've got negative 7, negative 5, 2, and negative 1, and then 2, negative 3, 7, and 35. So really what I've done is I've taken that augmented matrix, and you can see that each of the columns in my augmented matrix represent the columns, those column matrices that I've got up above. So another way I could think about this is if I want to keep it intact as a single matrix, I could literally just draw lines in my matrix to show that I've partitioned it into 4 separate columns. Now, you can do this any way you want to. If I want to, let me just undo this. I could partition this matrix to look something like this, or I could partition it to look something like this. And you can partition a matrix any way that you want to. Now, there's a lot of mathematics then that we can do with this in terms of like how do we multiply partition matrices and things like that. We're not going to get into that. That's not one of the things that we want to get into in this course. But I want you to just be aware that that is a possibility. And especially when we're using large matrices, Partitioning can serve a lot of different purposes. For example, partitioning could allow us to take a matrix that may have data that represents more than one idea and partition it into the different pieces. So this upper left quadrant might have data that means something different than this data, that means something different than this, and so on. So partitioning could be for that reason. Partitioning is also helpful in doing some of that math for really large matrices in smaller pieces in ways that are easier to manage. So like I said, we're not going to get into a lot of that, but I do believe that there is one problem that you're going to see in your book where you are going to multiply two smaller partition matrices together, and your book will, right before the example, will show you how to do that. And it's quite an interesting technique or method for doing that. But basically the point is that, again, if we think about if you had a matrix with thousands, perhaps millions of data points in their entries in there, and you multiply it by another matrix of a similar size, the math behind trying to do that, if we just did row times column, row times column, row times column to get all of the entries in that multiplied matrix, would be just ridiculous. Partition matrices allow us to break it down. It's still a lot of work, but it allows us to break down those matrices into smaller chunks that are a little more manageable, where we can find a piece of the answer and then we add to it another piece of an answer. We add to it another piece of an answer. So it's still going to be a lot of work, but it allows for better management of the data and of the process in general. So like I said, that's all I want to kind of do with partition matrices, is make you aware of them. And like I said, you will do a little bit of that work in your exercises that will just enhance your understanding just a little more as to why we might want to partition matrices and what the purpose is of that. So that's it for this lesson, and I will see you in the next.